Hello and welcome to this presentation on understanding the Heisenberg effect of spatial interaction, a selection-induced error for spatially tracked input. This work was conducted with my colleagues Jan Guggenhammer, Marco Kombosch and Enrico Ruccio from Ulm University. The term Heisenberg effect of spatial interaction was beautifully coined by Doug Bowman, and the definition is that a user wants to select an object using ray casting. She orients the ray so that it intersects the object, but when she presses the button, the force of the button press displaces the ray so that the object is not selected. To clarify what this means, I have a very exaggerated example of a button press and the following displacement. So using this valve controller, you can see that whenever I press the trigger button, my controller gets displaced upwards. If we now imagine that I'm pointing at a target that I'm trying to select and I'm doing the trigger press again, my selection ray gets displaced and I end up outside of my target or selecting something totally different. We coined this the Heisenberg error. So we started the selection within the target, but we ended up outside of it. The difference between the selection vectors you can see here is what we call the Heisenberg magnitude, so the angular offset that we end up with. We were very interested in finding out how this Heisenberg effect impacts the selection performance. To this end, we conducted a within-subject user study with 16 participants, and we gave them two tasks. The first task is a standard pointing task, or what we call the ballistic task, where participants have to select disks that are shown at 8 meters in front of them. Additionally, to collect data on the hand jitter and the pure displacement of the selection when pressing the button, we collected so-called stationary data. So participants were asked to stay within the target after their ballistic click until the indicator turned green and then perform another click. This way we could collect their hand jitter during the timeout and we could get the raw displacement of the button press. We were also interested in how input parameters could influence the Heisenberg effect. To this end, we used body posture, so standing and sitting, arm posture, an extended arm and an applied arm, and the degrees of freedom, so using 6 degrees of freedom or 3 degrees of freedom. We had different measurements that we took. Some of them are the overall error, so this is the total amount of errors, meaning that the percentage of targets that were missed. Then the Heisenberg error, just the percentage of missed targets where the selection started within the target but ended up outside of it. The Heisenberg magnitude, which is the angular offset between the selection start and end whenever a Heisenberg error occurs. The click duration, so the time it takes for the trigger press to finish, so to reach this final click where the click event is sent to the software. And we also calculated effective throughput as proposed by Sokurov and McKenzie to see the impact on the performance. What we found is that the Heisenberg effect expressed a systematic upwards shift. The direction of this shift could be due to the button position that we used. So the valve controller has a trigger button on the bottom, meaning that another position of the trigger or another button could lead to another direction. This has to be explored in the future. We also found that the Heisenberg error, remember the error that happens when a selection started within the target but ended up outside of it due to the displacement, was higher for smaller targets, but the Heisenberg magnitude reduced with the target size, meaning that the visual representation of the target did indeed influence the selection behavior of the participants, which is very interesting. We also found a nearly linear relationship between the trigger press value, so how far the trigger is pressed in, and the angular offset or the Heisenberg magnitude. So the further the trigger was pressed, the more the ray or the selection ray got displaced. We didn't find any significant difference for body posture, so standing or sitting didn't obviously affect the selecting arm. We did find a difference in the click duration for the arm posture. So an extended arm led to a shorter click duration, which might be due to the tension in the muscles. And we also found at the end that click duration was correlating with Heisenberg magnitude. So a longer click or longer selection would lead to a higher angular displacement or higher angular offset. We also found, surprisingly, that 6 degrees of freedom led to a lower Heisenberg error than 3 degrees of freedom. This could be explained due to the behavior of our participants, which didn't change between 6 degrees of freedom and 3 degrees of freedom when selecting, meaning that participants used their arm during the 3 degrees of freedom condition instead of just using their wrist. Now that we know that the Heisenberg effect does indeed exist and that it impacts our performance, we want to know, how do we deal with this? How can we compensate this effect, or how can we avoid it? The first initial, maybe naive thought might be that, okay, we know that we started pressing the button at a certain position. Why not go back to that position? Well, if we look at where the participant started clicking or pressing the button, we can see that it usually happened outside of the target, especially for the ballistic condition, which is closer to reality, where we have our movements during our selections. We can see that even for the largest targets, we still had 37.4% of selections that started outside of the target. So accepting this initial press position as the final selection would lead automatically to an error of at least 37.4% in the conditions we used for the target sizes we used. This is higher than the Heisenberg error that we observed in the ballistic condition, and this is almost as high as the overall error, so the overall missed targets. Another strategy might be to go to a position before the click happened. We have seen that the relationship between the trigger press and the offset is almost linear. So if we use a trigger press value lower than 1, we might end up with less displacement. The problem here is that for the almost 20,000 selections that we recorded, we also recorded over 17,000 so-called forced trigger presses. That means that participants started pressing the button but released it again without fully clicking, which might be due to unintentional finger movements, so-called nervous trigger finger, or other issues. So if we look at the cumulative histogram of the forced trigger presses, we can see that 95% of them happened for a trigger press value below 0.83. So if we accept this trigger press value, which is up there, and we go back to our trigger press value relationship with the offset, we can see that we could go from a displacement of 0.66 degrees down to 0.53 degrees. Another compensation strategy could be to use larger target sizes. So use targets that are large enough to compensate for the Heisenberg magnitude. If we look at the cumulative histogram of our data, we can see that even for the largest targets that we used, 95% of the Heisenberg errors happened below a value of 1.7 degrees. So the Heisenberg magnitude was on average 1.7 degrees for this target. So if we do use this value to calculate the targets that are necessary to be large enough to compensate for this magnitude, we can see that the targets have to be rather large. And this is for the ideal situation that the participant is pointing at the center without any hand jitter whatsoever. So the targets would need to be even larger, which is totally impractical for real life. So what we propose as the final solution is to use a correction function. To this end, we collected the data of our offset vectors that happened globally, so disregarding the conditions, and by condition. So this is what we call the global correction and the groupwise correction. If we look at the Heisenberg error, we can see that using a global correction, so just use the offset vector or the correction vector that we calculated that anybody out there could use, or anybody who uses the same trigger button, the Heisenberg error could be reduced by 19.5%. And if we have information on the condition, so the body position, arm position, and degrees of freedom, we can even go down to 25.5%, or reduce it by 25.4%. And getting this information is not that hard. If you think about it, body position is just the HMD position. We can derive that from the height of the HMD position. Arm position can be derived from the relative position of the controller to the HMD, and degrees of freedom are given by the platform. This way we can even correct the overall error by either 8% with the global correction or almost 12% with the groupwise correction. So to sum it all up, we have found that there is a systematic directional shift, in our case upwards shift with the Heisenberg effect. It does indeed impact selection precision and the performance, so the throughput. The posture of the arm and the body was largely irrelevant for the Heisenberg effect, but we did find that the degrees of freedom do impact the Heisenberg error, where 6 degrees of freedom led to a lower Heisenberg error. And that the Heisenberg effect can be compensated by different strategies, for example, a time shift, so going back to another selection position, using a lower trigger value, using larger target sizes, or just use a compensation function, which can happen in software. Thank you very much for listening to my talk. My name is Dennis Wolf, and I will be happy to take any questions. You can contact me via email or on my website. Thank you.